Every discovery begins with a new way of seeing. NASA's Nancy Grace Roman Space Telescope will reveal the universe on an unprecedented scale. With its powerful, wide-eyed view, Roman will map vast regions of the cosmos, capturing millions of stars, planets, and galaxies. By observing the sky again and again, Roman will create time-lapse movies of our dynamic universe. It will seek the hidden influence of dark matter and uncover the mysterious force driving the universe's expansion. With a wider view comes a deeper understanding. Welcome to NASA's broadest view of the universe.
Hello, everyone, and thank you very much for joining us. I'm Elise Fisher with NASA's Office of Communications, and we are here live from the agency's Goddard Space Flight Center in Greenbelt, Maryland, where NASA built its next major eye on the universe, the Nancy Grace Roman Space Telescope. In our news conference today, you'll hear from our experts all about Roman, which is right now undergoing final preparations for a launch next month from our Kennedy Space Center in Florida. And when its mission begins, Roman will tackle some of the biggest mysteries about our universe today, from dark energy and why the universe is expanding faster over time, to planets outside our solar system. So to tell us more about Roman and to take your questions, we have with us Shawn Domagal-Goldman, Director of the Astrophysics Division at NASA headquarters, Julie McEnery, Roman's Senior Project Scientist at NASA Goddard, Jackie Townsend, Roman Project Manager at NASA Goddard, and Jeremy Perkins, Roman Integration and Test Scientist, also at NASA Goddard. We will hear briefly from all of our panelists first off the top, and then we will take questions from media who are listening on the phone lines. So I'll start by turning it over to Shawn.
Thank you, Elise. I'm so glad to be here today to talk about this telescope, the Nancy Grace Roman Space Telescope, because it's a big part of our history and how it connects to our future. NASA's had a long history of leading the world in exploring the cosmos, and in astrophysics, we do that by probing some of the most fundamental questions to humanity. How does the universe work? How do we get here in that universe? And are we alone in that universe? And we can do that because of the power of astronomy from space. That capability is in many ways thanks to the person that this observatory is named after, Dr. Nancy Grace Roman. Dr. Roman was a brilliant astronomer, and she realized how much power we would have if we could get telescopes up above Earth's atmosphere, which otherwise gets in the way of our observations from the ground, and how it could complement the astronomy we can do from the ground. She had the technical acumen to detail those arguments and the leadership and political capability to explain that to her peers and to stakeholders. And although she's often most associated with those first space telescopes, it's really our full fleet that she deserves credit for. And every time we build a new space telescope, we add to that fleet with capabilities we didn't have before and that add to her legacy. And that telescope, that's her namesake, the Nancy Grace Roman Space Telescope, is no exception. The best way I could describe how it's going to add to our fleet is by going through an extended analogy of someone taking photos of a forest. By getting telescopes up into space, we can have the sharpness that let us not just take pictures of the forest itself or the trees, but in some cases the leaves or the birds in those trees. That's what we did with Hubble. With the James Webb Space Telescope, we could take pictures of those birds and leaves and further off trees. And with our survey telescopes like SphereX, which we launched last year, we can take panoramic views of the forest itself. Roman does both. It has that wide-angle view of the forest and the sharpness to see the birds and leaves on those trees. Of course, this isn't a forest we're talking about, it's the known universe. And those birds and trees are supernova and galaxies and planets and stars. In many ways, the astronomical target that Roman is chasing and designed to study is the universe itself. And when it launches, it's going to do things that currently are impossible. And it's going to launch, thanks to the folks here with me and people throughout the world, 9 months in advance. And that in of itself is an amazing feat. You know, just think about any large project you have in your town or anywhere that's multi-billion dollars. Complex things are hard to bring in on schedule and on budget. And this team has lived within its resources and is delivering 9 months early. So I'm thankful for the people here with me on stage, the full team across the world that they led. And there's far too many people to name, but I do want to thank the institutions that have been a big part of this. Of course, the folks here at NASA Goddard Space Flight Center that led the development and management and built major parts of this observatory. Our partners from NASA's Jet Propulsion Labs, the Space Telescope Science Institute, IPAC, BAE Systems, L3 Harris, and Teledyne Science and Imaging that either delivered hardware and or are going to be part of our operations that you'll hear about later today. And of course, I want to thank our international partners from the European, Japanese, and French space agencies, as well as the Max Planck Institute for Astronomy in Germany. Space is hard. Doing space on time and on budget is even harder. And this takes a team, and we've got a fantastic one that I just mentioned that's gotten us to this point. And I'm thankful they have. And this is one last way that this is going to connect our past to our future, because the questions we ask in astronomy, I said, you know, there are these big questions. And when we launched Hubble, we did that in many ways to study the expansion rate of the universe. And we answered through Hubble some of the biggest cosmological questions we had at the time. But in finding the answers to those questions, we uncovered new questions to answer. And some of those questions are the ones that Roman is designed to tackle. And that's why I'm glad we've got a fantastic science team led by Julie McEnery, who can tell you more about the science from Roman.
Thank you, Shawn. Roman is poised to conduct revolutionary surveys that will impact every area of astronomy. We perform an extraordinary census of planets around other stars and may confirm the current hints that our standard model of the universe is incorrect and set us on the path to figuring out what's right. And we can do this because Roman's primary instrument combines exquisite performance and sensitivity with the ability to quickly and efficiently survey large regions of the sky. 1 month of Roman observations could survey our own Milky Way, resulting in the detection of up to half the stars in our own galaxy. This would itself represent a catalogue of astronomical objects much larger than any in existence today, with just 1 month of Roman observations. Our main survey will take over a year, and it'll be really huge. We would need over 500,000 4K TVs to fully display the single Roman image from our largest survey. To understand the scale, these TVs would cover 45 Manhattan city blocks, or fully cover El Capitan in Yosemite National Park. Not that I'm suggesting that we should actually cover El Capitan, but you get the idea. This survey will contain over 2 billion galaxies and will enable us to study how the structures in our universe, the stars, the galaxies, the clusters of galaxies, grew and evolved. We'll also measure how our universe has expanded over time. And these are the keys that will allow us to unlock the fundamental nature of dark matter and dark energy and the fabric of the universe itself. Our universe puts on spectacular cosmic displays every second, but these events happen very quickly and often elude our telescopes. With Roman's panoramic vision, we'll not only catch these events, but see several at once. We'll identify tens of thousands of supernovae and use these as markers to track the expansion history of the universe. We'll detect bright flares as a star is swept into a supermassive black hole. And we'll see the extraordinary outbursts that occur when 2 neutron stars merge to form a new black hole. Periodically, Roman will turn its sights toward the center of our own galaxy and monitor hundreds of millions of stars in a small patch of sky every few minutes. But it won't only image millions of stars. It will discover a host of new exoplanets, up to 40 times more than we know of today. Think of this as the largest census we've ever done of planets outside our own solar system. Roman's vast reach will allow us to find the weird, the rare, and the unusual. Discovery of things like exoplanets with disks, isolated black holes and neutron stars in our galaxy, and runaway supermassive black holes will become routine. We'll redefine what it means to find a needle in a haystack. Scientists across the country, and indeed the world, have worked together to figure out the best way to conduct Roman surveys. This is important because every single Roman observation will enable many different science investigations. So, for example, the same survey that will provide deep observations to study galaxies will also be used to find objects in the outer parts of our own solar system. We have a second instrument, the Roman coronagraph. And I think of this as doing magic with physics. We're taking advantage of the wave properties of light to cancel out the light from a star so that we can image planets next to it. To do this magic, we have to have an optical system that can adjust itself to maintain sufficient precision. And this will be the first time that this kind of active optics has been used in space and will set us on a path for future observatories to do extraordinary new things. What makes me most excited about Roman is the discovery potential. With 2 billion galaxies, we'll have 2,000 objects that are 1 in a million. We'll be exploring patches of sky as a function of time with exquisite sensitivity. We'll find new things that go bump in the night. I very much hope, and in fact expect, that the most exciting things from Roman will be a surprise, something that we couldn't predict, but will set the stage for the next deeper set of questions for future missions to address. And now, Jackie will continue the story.
I find Julie's talk so inspiring, but she's an incredibly tough act to follow. So I do have the privilege to report that the project is right where we need to be as we approach launch. We're at L-31 3/4 days, and it's starting to get incredibly exciting. The flight segment is ready to go. The amazing team that completed the development to be ready to launch 9 months early, as Shawn indicated. No surprise, they've stayed right on schedule with the work down at the Kennedy Space Center. The observatory was fueled last week, and we're about to start our joint operations with the SpaceX launch vehicle team to complete the preparations to mate the observatory to the Falcon Heavy rocket. Encapsulation, which is when the observatory is installed into the fairing that will carry us to orbit, that happens in 3 short weeks. The ground segment is also ready to go. In early July, we completed a really successful review of our readiness to begin operations. That's to launch the observatory, commission it, and then start science operations downlinking up to 11 terabits per day, every day. And the science team is ready to go. The whole team is ready to go. We've practiced and tuned up the plans and the procedures, and training the staff with 50 mission readiness tests encompassing more than 1,100 hours of operational time, using the exact staff who were going to be on console during launch and commissioning across the first 100 days. So the Roman Dream Team continues to do mighty things, and I am delighted to say yet again, Roman is ready for launch. And with that, I will hand it over to Jeremy to talk more about commissioning.
Thanks. It's been an incredible journey to get Roman to this point. And like Jackie said, it's been the work of an amazing group of people around the world and the country to make sure that we're ready to go. And I've been very lucky to be part of this team. In just a few days, in 30 days, we're going to be launching Roman, testing it out, opening the deployable aperture cover, looking at the sky, and sending data down to the ground for the first time. But we still have a lot of work to do right after launch. One of the things that you think about, and you probably have in your head when you think of NASA, is a bunch of engineers and scientists sitting in a room staring at a bunch of computer monitors trying to solve the hard problems that space has thrown at them. And we're almost to that point with Roman. Right after launch, lots of us are going to be sitting down in Florida and up here in Maryland and out in California, monitoring our systems and making sure that Roman is operating like we know it can. It's taken a lot to get here. A lot of planning, building, testing, and practicing, sometimes in windowless rooms, and sometimes in clean rooms, in labs, and in universities, and at scientific meetings around the country and around the world. So SpaceX should put us in a really good orientation after we separate with our solar panels pointed at the sun and our instruments safely on the other side of the observatory. But right after separation, we're going to be activating Roman, and it's going to be actively making sure that our solar panels are going the right way. We deploy the side panels and the sun shield, and we start checking out the propulsion system. Right around the end of the first day, we use that propulsion system to make sure that we get sent in the right direction towards Lagrange point 2, about 1 million miles from Earth. And it's going to take us about 100 days to get there, and we're going to use that time to make sure that we're ready to go and do all the science that Julie talked about. And just as an aside, we've been practicing this over and over and over again, especially the launch and the first day part. This team is more than prepared for what's going to happen during launch and commissioning. After the first day, the next couple of weeks are also going to be busy. We check out all the subsystems. We check out the power system, the pointing system, the data management system, I mean everything. And we look at it all with a fine-tooth comb. The people that built and tested and delivered Roman are the same folks that are going to make sure it's working as we expect it to on orbit. And all of this is while Roman goes out past the orbit of the moon and on to L2 a million miles away. During this time, we also open the telescope to the sky and we check out the instruments for the first time. An important thing that happens during this time as well is that we deploy the high gain antenna. This is the antenna we use to send all of our data back to Earth. It's about as wide as I am tall, and it's been folded up underneath Roman since it left Goddard up here in Maryland earlier this summer. To really do the science and the bold discoveries that Julie talked about, we have to get a lot of data back down to Earth. We basically never stop taking images of the sky, and our images are really big. We're talking about sending about 1 terabyte of data down to the ground every day. This is kind of like streaming a million songs from a million miles from Earth down to Earth. That's more music than I'll probably listen to in my whole life. Later during commissioning, we're going to be really streaming data hard down to the ground. And we've practiced this over and over again on the ground by sending data up to our partners in Baltimore and out in California to make sure that all of our systems are ready to go. But before we start doing that, we need to make sure the telescope is aligned and sending down the most pristine images we know this machine can actually accomplish on orbit. And we use the sky to do that. We look at actually the stars and measure how big they are and adjust our telescope to make sure it has the best pointing possible. And I feel like a broken record, but we've practiced this over and over and over again at sites out in Boulder, Colorado, up in New York, and in here at Goddard as well. But now, at the end of commissioning, we get to the phase where scientists start digging into the data. We basically do many versions of our calibration plan and our observation plan at this time to really fully test the system out and make sure we're going to be able to do the science operations at the end of the commissioning phase. One thing to keep in mind is once we start science ops, no single person is going to be able to look at all of the stars and all the galaxies and all the unusual things that we're going to see with Roman. One way I like to think about this is our data set at the end of Roman's life is going to be bigger than your favorite music streaming platforms. And I can't go online and listen to every single song to find new songs and new music. I have to use algorithms and other ways to introduce new music to myself. And we're going to do the same with Roman. And it's important to remember that some person's noise might be my music and my music might be noise to other people. But it's going to take detailed analysis, machine learning, and computational systems to really find the music in Roman's data. We're using this early time, this commissioning time, to shake out all the techniques, to find the gotchas, find the bugs, and basically do the early calibrations we need to do so that we're ready when the torrent of data starts. The teams that are going to be producing Roman science data for years to come are going to be side by side with us in the commissioning rooms, making sure that they're ready to analyze Roman's data. To do this, we're going to look at fields of stars and make sure we have the alignment correct. We monitor how big the stars are to make sure we have the focus correct and that it's not changing with time. We run lots of calibrations and compare those with the tests we did on the ground to make sure everything looks okay. We make sure that the telescope is dark enough for the science that we want to do, and we make sure the telescope is stable enough so that we know how fast we're going to be able to do our science. Scientists working in Roman have spent years developing this plan and thinking about all the little details to make sure we get it right. And thousands of people have designed, built, and tested Roman, and so many people are waiting to see what Roman can do. We're going to be working around the clock over the next months to make sure that what we built works the way we planned it to. I think I speak for all of us. We're really excited to see Roman launch, but we're even more excited to see the first light hit the telescope. Thank you.
Great. Thank you so much, Jeremy, and thank you all for those comments. And with that, we will now begin taking questions. So for media who are listening on the phone lines, you can press *1 to enter the queue. And we'd ask that if you know who you'd like to direct your question to, that you please note that as well. Again, that's *1. And we will take our first question on the line from Marcia Dunn with the Associated Press. Go ahead, Marcia.
Thank you. Hello. for one of the science types. I'm wondering, what specifically can Roman do or see that Hubble and Webb cannot? And I also know Roman will be quick about its work. If Roman can scan the entire Milky Way in a month, as I think you referred to just a little bit ago, how long would it take Hubble or Webb to cover the same territory? Trying to get a comparison between the three telescopes. Thank you so much.
Okay, so Roman has broadly the same sensitivity and sharpness of vision as Hubble, but we survey the sky much faster. So that 1 month of observations to survey our Milky Way galaxy would take about a century with Hubble. So that's the edge that Roman has over Hubble is our ability to sweep out large regions of the sky. That opens completely new science questions for us to address. Our comparison with Webb is a little bit different. So Webb is designed to be able to probe very deeply and with exquisite sensitivity into the universe. So it can find rare things in the early universe. But you need Roman to find rare things in the more nearby universe. So for example, one of the discoveries with Webb is little red dots, these small point source objects. But Webb isn't able to find enough of them nearby to figure out how those red dots evolve. And that is something that Roman can address. So basically, we provide the large vision that complements the deep views that Webb provides.
Great. Thank you, Julie. Our next question now is from Stephen Clark with Ars Technica. Go ahead, Stephen.
Thank you for taking my question. My question's on the mirror for Roman. This mirror was donated by the NRO more than a decade ago, and I know that drove some of the design constraints into Roman. And I'm curious for any perspectives on that. Did that result in cost savings, or did it drive up costs on Roman in the end? Just some of the trade-offs around that. And related, what are your plans for the other mirror that was donated by the NRO to NASA? Thank you.
You take the first part. I'll take the second.
So in terms of cost savings, the transferred telescope was in our baseline cost when we got the cost cap. So the assumption that that was in there cannot be credited with any of the cost performance that we have to date. And I think the benefit of that telescope was it forced the whole team, the science team, to close those trade studies and define the architecture early enough that we could make smart decisions and move forward instead of getting bogged down in design cycles that can end up costing more money. And
the short answer is there's no current plans that NASA has that I'm aware of.
All right, thank you very much. And right now we are working an issue with the phone line. So while we are waiting, I'm wondering if, Julie, you could tell us a little bit more, coming back to this question about comparing Roman versus Webb and Hubble, and tell us a little bit more about some of the ways that our telescopes provide science questions that we didn't even think of yet. What surprises might you envision when we think about the sheer volume of what Roman can do?
Well, actually, I think an interesting example of that is, Roman was motivated in part by the discovery in the late 90s that our universe isn't expanding at a steady rate. It's not decelerating like you might expect from gravity acting on the matter in the universe, but it's actually accelerating. And that's an incredibly exciting thing to study. But in the time between then and now, it's become even more exciting because we have a straightforward, in a cosmological sense, a way to explain how the universe works that really, really well connects what we see in the early universe with the cosmic microwave background to what we see now today. So we map the expansion rate, what structure should look like. And that had been fantastic, but there have been hints in the last 5 to 10 years that all is not well with our standard model. There are hints that the Hubble constant, which describes the expansion of the universe is not quite consistent or not as predicted by this model. There are hints that the distribution of matter, the structure of matter in the universe is not quite right. And there are even hints that the cosmological constant, a constant property of space-time, is in fact not constant. And all of these mean that Roman's observations are so much more exciting now, because we're probably not going to confirm a standard model of how the universe works. We're very likely to demonstrate that our standard model is wrong and to set ourselves on a path to figuring out how does our universe really work. And it's hard to get better than the fundamental nature of your universe.
Awesome. Thank you, Julie. And we do now have the phone line back, so we will go ahead and take our next question, which is from Marina Corin, who is freelance. Go ahead, Marina.
Hi, thanks, Elise. This question is for Shawn and Julie. I'm curious about Roman's galactic bulge time domain survey, which NASA says will provide one of the deepest views ever into the heart of the galaxy. What does that actually mean? And I don't want to focus on exoplanets there, but more broadly, what does it mean to get a really good look at the center of the Milky Way as a cosmic environment in its own right? And how will those observations of the galactic center compare to others that have been done before Roman? Thanks.
I would take the exoplanet part, so you go on this one, Julie.
I'm really glad for this question because it allows me to illustrate two things. So the original motivation for the Galactic Bulge Time Domain Survey was, as you suggest, Roman's revolutionary observations for exoplanets. And what this survey does is we have a patch of sky, and every 12.5 minutes, we're going to monitor several 100 million stars. But in the national and international community-based process for how exactly do we want to conduct those observations, we actually moved one of the fields to be exactly on the galactic center itself, so right on the supermassive black hole that's at the center of our galaxy. So that survey is also going to monitor all the extraordinary things that happen around the supermassive black hole in the center of our galaxy. These observations that happen every 12.5 minutes, we're going to be doing it for an entire year. So when you add all of this data together, you're going to have one of the deepest views ever. And because we're operating in the near infrared, we get to penetrate right to the center and actually beyond to the other side of our galaxy. So we will be able to study things like the individual properties of stars from astroseismology, so to look at how the pressure waves within stars produce changes in their brightness. We'll be able to study populations of stars right at the galactic bulge to explore things like the distribution of dark matter and probe sort of the history of the Milky Way in those regions. And there's much more. It is going to be an amazing data set.
All right. Then we'll go to our next question on the phone. That is from Jeff Faust with Space News.
Hey, good afternoon. Question for Jeremy. Apologies if I missed it, but how long will this commissioning process take place after launch until you're ready to start normal science observations with Roman? And then also, all this data you're downlinking, are you using the DSN or will you have a dedicated ground station for the Roman data? Thank you.
Yeah, sure. So it takes us about 100 days to get out to L2. And we're projecting it's going to be about a 3-month commissioning process that we have planned out, give or take, depending on how things go and what we find when we get up there. And then we have dedicated ground systems to get the data down. We do use DSN for commanding and for telemetry, but then we use some dedicated ground systems around the world to get the data down using the high gain antenna.
Y'all are going to help us celebrate the new year, is what I heard.
Yeah. Yep, and there's many exciting things, so yeah.
All right, thank you. We can take our next question from Bill Harwood with CBS News. Go ahead, Bill.
Yeah, thank you very much. This is a follow-up on Stephen Clark's question about the mirror. When NASA took delivery of this mirror, was it delivered to you fully tested and you built Roman around it, or what sort of testing, if any, did you guys do to verify that it, was going to have the performance you wanted. I'm just curious how it came to you and what you did after you got it, if anything, to the mirror. Thanks.
I think Julie's going to answer that.
Well, I can answer some aspects, and you can follow. So we needed to refigure the telescope to slightly change the optical prescription. We needed to change some of the structure so that it could operate at lower temperatures. It certainly wasn't just plug and play.
Yeah, I think our engineering team thinks of it as we received a set of well-tested parts that included highly calibrated optical systems, but we really had to sort of start over and make it our own to work at our operating temperatures and for our particular field of view. So hopefully that's enough of an answer.
Yeah, and I think just to build off that a little bit, for our biggest flagship observatories, they're custom designed and built and then operated to achieve something that nothing else could.
Yep.
And that goes into every literal nook and cranny of the observatory, including the shaping of the mirror. Taking things in a plug and play mode is something we do on our smaller, faster missions more often than on a big flagship. So this one did take, and any future flagship that we took on, some part that we received would also have to go into the same customization, effectively.
Thank you. Next up, we have Jim Siegel with Space Insights.
Hi, everybody. Thank you for doing this, and congratulations on your success so far. Looking forward to the launch next month. How many people at NASA are going to be involved in the ongoing operation of Roman when it becomes operational? Where are they located? And secondly, for my typical viewers, how would I describe the benefits to the average American, that is Joe and Sally lunch bucket, so to speak, of what the Roman means to them? Thank you.
So in terms of the folks working during operations, we have an operations team that's made up of dozens of folks. But then if you think of the wider group of people that are actually working on Roman, it's going to be hundreds to thousands, because the data sets that we produce are open to the whole country and the world. And the folks that are going to be looking at Roman's data and doing science with Roman is almost uncountable in terms of the reach that we're going to have.
Do you want to name some of the primary locations?
Yeah, so we've got teams up in Maryland, both at Goddard and then up in Baltimore, and then out in California at IPAC and JPL, as well as universities around the country that are also working on Roman's data. Yeah.
Do anyone want to take the answer for Roman specifically, or I can take it for the portfolio in terms of what it returns to all the folks out there?
I can answer quickly, and one of the reasons that I think is something that's awesome about Roman is that because our data are immediately available to everybody in the country at the same time, that you can be a teacher in a high school in Kentucky, and your students have the opportunity to see Roman data, new Roman discoveries at the same time as a professor in Princeton. And I think that there's a place for helping people get really excited about the amazing things that we're able to build.
Yeah, and for me, I think this comes down to two things. One, the first thing I said is, in NASA Astrophysics, we pursue the big questions. Are we alone? How do we get here? How does the universe work? And Roman's going to help us answer those really curiosity-driven questions. Like we're nerds. Like we're NASA. Like we love that stuff. That's why we do this. But when we do these things, especially for the flagships, we're setting out to do stuff that's like not possible. Like the stuff we're going to do with Roman isn't possible today. It won't even be possible when we launch it. It won't be possible until we're done with the commissioning and it's like well-tuned, right? When we set out to do the impossible and then achieve it, it's not just our impossibles that become possible. Like to give an example, when we built Hubble and Webb, we were chasing far-off galaxies in the farthest corners of the universe. But because we have a Hubble and a Webb, we're able to track asteroids that would pose a threat to Earth or to future lunar outposts on the lunar surface, right? Those were impossibilities that are now just possible and sometimes routine. There's things that go into medical imaging devices in our cell phones that come out of stuff that was impossible until NASA did it. And now it's so routine you carry it around in your pocket. So, we're nerds. We chase the curiosity-driven impossible stuff, but we make a lot of other stuff routine that impacts our daily lives in many, many ways.
All right, then we can now take our next question from Manuel Mazzanti with Exploración Espacial.
Thank you so much, Manuel Mazzanti with Exploración Espacial. This is a question probably for Jackie or Julie. Once the telescope is ready to go and operational, how NASA prioritizes observations? Is there a set of objectives that NASA wants to achieve first? How is it that an astronomer, a scientist, can get to use the telescope? I imagine presenting a proposal. How long does it take? We are talking about weeks, months, years to finally use the telescope. Thank you.
We're an unusual kind of telescope. So our model isn't the traditional astronomers write proposals and get time on the telescope and go off and do things. I mean, we do that as well, but that's not the primary way to use Roman. So what we did over the last few years was to work with the scientific community all over the world and ask them for their ideas on how we should use Roman. And then we put everything together to try and design 3 really large surveys that address the cosmology, that address the exoplanet studies, but that maximize the science. So one outcome of that was putting one of the fields for the galactic bulge time domain survey at the galactic center. That was motivated by scientists in the community telling us this is how you make best use of this survey. One of our other surveys, we're going to do a deep field. And the purpose of that deep field is to provide the data needed to understand the specifics of how we measure galaxies, but we're choosing to collect the data in a way that maximizes our ability to find objects in the outer solar system. And that was because we had a white paper from members of the community who were interested in solar system science. So the quick answer is that we've actually already done the work of figuring out mostly how the telescope is going to be used. All the data immediately go public. We're seeing a large fraction of the sky. So almost regardless of what your scientific interest is, Roman is probably already planning to take observations. And the data that you need to conduct your scientific investigation is already planned to be immediately made public.
All right, thank you. And as a reminder, if you would like to ask a question, you can press *1 on the phone lines. But we will go next to David Deneau with About Space Today. You can go ahead, David.
Well, AST, our About Space Today, has an older age demographic. So in layman's language, how will the Roman Space Telescope benefit all mankind? A question for each of you from your positions.
Who wants to go first?
Everyone's looking at me. So I think the main thing is something I've already talked about. I think that the data set that Roman is going to produce is something that will not just benefit the science teams that are thinking about how to use it now, but they're going to be a benefit to the students in 5, 10, and even 20 years. Folks are going to be looking through this data for answers that they can find with Roman's data that they just don't know about today, that we haven't planned to use the observatory for. So that's kind of what I'm really excited about, the legacy of the data set that we're producing.
I'm ancient, so I may be in your demographic. I've been here long enough that I watched Hubble's findings change our understanding of the universe and change the textbooks that I was using to study in college. So I am, as Julie mentioned, I'm truly excited about the way that it's going to change our understanding of the universe. And in doing so, the next Dr. Nancy Grace Roman sitting in a classroom somewhere next year will be studying our data and hopefully catch the science bug and go on to transform the world in the same way that Dr. Nancy Grace Roman did. I could not be prouder to be part of this project.
I think exploration is important. I think as we explore things, we discover new places. In this case, we're going to be discovering new places remotely with the data that we find from the Nancy Grace Roman Space Telescope. But it is exploration. It's pushing the boundaries of our knowledge in ways that we now can't predict. And we now can't absolutely say what the long-standing legacy is. But I think it's nations that have been successful have been curious, have explored beyond their boundaries. And what we do with Roman is a very good example of that.
So I said a few minutes ago, when we set out to do these flagships, we set out to do the impossible and then make them routine. And one I didn't mention, but I want to build off of is the coronagraph instrument. That's one that Julie mentioned, doing magic with physics, right? And the technical challenge there is effectively to take a picture of a firefly next to a floodlight from the other side of the country, to go back to the photography example. The reason that's a critical technology for us to take from the impossible to we can do it now, is that's a stepping stone to doing the harder problem of taking a picture of that same firefly next to that same floodlight from the other side of the country, but with the firefly off. And now you're seeing the light reflected from the floodlight off the firefly's dark skin back at us. If we can do that second one, which Roman is a major stepping stone towards doing, we'll be able to build our next flagship observatory, the Habitable Worlds Observatory. And that's one that will look at not just stars and galaxies and understand cosmic evolution, but take pictures of planets next to stars and probe those planets for signs of habitability and of life, and really address the question of, are we alone? Are there other inhabited global biospheres like Earth out there? And that's, for me, I love that question.
Thank you all. That summed it up beautifully. We can take our next question on the phone from Paul Brinkman with Aerospace America magazine.
Hi, yes, thanks for taking my question. I'd like to ask about the propellant. NASA sent out a recent update about how Roman is fully fueled now. I think it's 1,100 liters. Seems like a lot more even than Webb. Can you talk about how that, why that's necessary, and how the station keeping of the observatory will compare to Webb, and how that relates to its wide field astronomy?
Sure. We use the propellant in a couple ways. The one I already mentioned was to do our mid-course correction, which is our first correction to make sure that we're going in the right direction to L2. We do have also enough fuel reserve to do another correction if we need to. And then, like you mentioned, we do a final orbit insertion around day 100 to get into our final orbit around L2. Then after that, we have enough fuel to do all of the momentum dumps and the station keeping maneuvers that we need to do for 5 years and more. So that's why we have all the fuel we put into the tanks last week to make sure that we last that 5 years and beyond. I don't know how that compares to Webb and other missions that have used similar systems. So we can follow up with you on that one.
Yeah, we can follow up absolutely after the fact. And thanks for the question. We can now go to our next one on the line, which is Ken Kramer with Space Up Close.
Oh, hi. Thank you. Thanks very much for doing this. And, we're looking forward to the launch, too. Yeah. So my question is about the coronagraph, actually. Can you describe, how will that work to find the exoplanets? And I imagine it's going to work in different ways to find them. So can you talk about that in some detail, as well as you're looking at such a wide swath? How is it able to find those exoplanets when you're not looking in a narrow focus and you're looking in a wide focus? Thanks.
Yeah, I can start, and then you correct me if I get any of this wrong, Julie or Jack. So the first place to start is the challenge with these is kind of that firefly floodlight analogy. The other way to think about this is if you're tracking a ball or a plane or a bird in the sky and it crosses over, or Superman in the sky and it crosses by the sun, you have to stop looking at some point, or else your detectors, your eyeballs will be literally overwhelmed with the sunlight, right? And it's the same thing. We're taking a picture of a very dim planet next to a very, very bright star. You have to block out the sunlight, or the starlight in this case, or else it'll overwhelm your detectors. And that's what a coronagraph does. Now, to one of your questions kind of has our design embedded in it, because you're asking, like, well, how do you do that if you got this wide field of view? Roman's designed with an instrument to give us, that's the wide field imager gives us that big view, that a separate instrument, the CGI, or the coronagraph instrument, that's the one. It's a different instrument with a different optical path that's going to be doing that blocking out of the starlight. Did I miss anything in that?
Well, I think it might be, what I find very cool about our coronagraph is that we're going to be demonstrating the use of deformable mirrors in space for the first time. And that is important to maintain the optical precision that we need. We're also going to have state-of-the-art wavefront sensing equipment. We will be testing a variety of different kinds of masks that will create destructive interference of the light, to use the wave properties of light to effectively switch off the light in the place where we want it to be. And then finally, we also have ultra-low noise photon counting cameras. So cameras that on the coronagraph that are optimized to find and be able to make measurements of very, very faint things. And all of these things combined are what we need to understand the technologies to take coronography to the next level.
Yeah, and can I add one more to that? Which is the telescope itself, right? Yes. So all the things that Julia's describing, those deformable mirrors, those are designed to basically impart the opposite error to the wavefront that the telescope is imparting. And the better your telescope, the more stable it is, the easier that job is going to be for the deformable mirrors in the coronagraph. And those things have to work in concert as well. And this is in part possible because we've got such a darn good telescope that it makes the job of the coronagraph possible. And also studying that all those interactions that Julia is mentioning, understanding those at the system level is also part of the unlock for HWL.
All right. Our next question on the line is from Lisa Grossman with Space News. You can go ahead, Lisa.
Hi, with Science News. Thanks for taking my question. A lot of the way that Roman works sounds very reminiscent of the way that the Vera Rubin Observatory works. Could you compare the two approaches? How are they different and complementary? Yeah.
Roman and Rubin have been designed from the very beginning to work together. They were both top ranked in the same decadal survey. They were designed knowing that each other existed, so they're complementary with one another. When we got to the point of deciding how we were going to use the observatories, Roman surveys are optimized to overlap with Rubin's because it is so valuable to combine observations with Roman and Rubin together. We're now approaching the next phase where scientists working on Rubin and scientists working on Roman are going to be directly working together to get the science. And the synergies are profound. Rubin operates in the visible, so in a further bluer light than does Roman, but to the same depth. So when you combine Roman and Rubin, it extends Roman's reach into the visible. Roman has much better angular resolution, so Roman can tell Rubin, that blurry thing that you have there, it's actually 3 galaxies, not 1. And when you put that information into the Rubin analysis, you end up with much better understanding of the universe that Rubin is studying. So we really are siblings embarking on a life of exploration at the same time.
And I might just broaden out on that for a second. Like, I think it's rare we have that degree of coordination, but every time we launch something into space, we're thoughtful in advance of how does this not just complement our space-based observatories, but what our colleagues at NSF or DOE or other science foundations around the world could be doing from the ground.
All right, thank you. We can take our next question from Marcia Smith with Space Policy Online.
Thanks so much for taking my question. Julie, you had talked about how you have already coordinated with the scientific community to develop these 3 surveys. Are those 3 surveys intended to be completed within the first 5 years, which is sort of the nominal lifetime, although everyone's expecting it's going to last at least for 10 years, and many of these telescopes last much longer. So how long will it take to complete those 3 surveys, and do you have a process already to look at what comes next if Roman keeps running?
So the quick answer to the first part of the question is yes. We have planned to complete those 3 surveys in the first 5 years of the mission. The answer to the second part of your question just makes me happy even thinking about it. So of course we're thinking about what you would want to do with more Roman observations. In our first 5 years, we have set aside time for Roman to do other things. So there are going to be other observations in addition to those 3 surveys. And we have, in fact, picked our first 6 so far. But I think what we want to do with an extended mission, what you might want to do after 5 years, is going to be very strongly driven by what we find in the first 5 years. We know there's exciting things to do because we know the things that didn't make the cut when we were defining those first 3 surveys. But my hope is that Roman makes dramatic new discoveries, and that the discoveries that Roman make help point the direction to, do we want to do additional really large, ambitious surveys? Or is it a better use of the telescope to have a larger number of smaller, more targeted things? And I think Roman itself is going to give us the information we need to address that question.
Great, thank you. Our next question on the line is from Will Robinson-Smith with Spaceflight Now.
Hi, thanks so much for taking my question, and apologies if my line breaks up. Question for Jackie and Jeremy. Jackie mentioned that there are about 3 weeks between now and when Roman will be encapsulated in the Falcon Heavy fairing. Now that the spacecraft is fueled, what is the primary focus from now till then for is complete? And there was also a mention of the amount of fuel on Roman, and that part of what it's going to be in service of is the correction maneuver. If the Falcon Heavy were to fly in an expendable configuration, would that remove the need for that correction maneuver, or would that happen regardless of whether the boosters are being reused or not? Thank you.
You want me to go or you want to go?
You can start.
So the things that we're doing now, Jackie mentioned that we're about to get into combined ops with SpaceX. And so the focus over the next 3 weeks is basically getting us onto all the adapter rings and into the configuration we need to be in to get mated to the rocket. So there's a few like closeouts and inspections we do as a team and together with SpaceX between now and then, but that's the main focus that we're going into now after fueling is over. In terms of the question about the expendable versus not, we would still probably have the mid-course correction, whether or not we did the expendables or not. And then in the end, it's similar to James Webb, depending on how good that push we get out from SpaceX means how much fuel we're going to use. And then also how good we do at that first mid-course correction determines if we need the second one.
And we would always have budgeted for them.
Yeah.
Great, thank you. We can take our next question from Colin Covington with Orbital Briefing.
Hey, hello. Thank you for taking my question. I think this is going to be a question focused towards science for Julie. And I'm wondering if Roman's measurements of dark energy significantly differ from current cosmological models. What would be the first implications for understanding of the universe?
So the quick answer is it will depend on the nature of what we find. So it might point towards a theory of modified gravity, or it might suggest that we need to alter our understanding of general relativity. But like I said, it kind of depends on the specifics of what we actually find, on whether it is staying broadly within the same family of cosmological models and just adding a little bit more complexity, or we're really blowing things out of the water and rethinking from the beginning.
All right. Our next question on the line is from Kyle Averill with SpacePoint. Go ahead, Kyle.
Thank you very much. Thank you for the opportunity and the opportunity to ask the question. Considering the terminology fleet, complementary, synergy, I'm wondering if it's really appropriate to start thinking about these platforms as an ecosystem, potentially. And then the second part of my question is, after Roman's two primary objectives, dark energy and ecoplanets, it will probe black holes. Does this effectively expand the complementary value of Roman to leverage the investment in science in LIGO, for example? Thank you for the question.
You want to take the last one? I'll take the first one.
So, complementary science with LIGO is not, at least in my opinion, it's not an add-on. It's not a thing that we're doing after we do studies of exoplanets and cosmology. It's an integral part of our program. We have the capability on Roman to redirect the observatory to follow up on the location of a LIGO detection. One of the things that we're looking for with LIGO detections is merger of two neutron stars, or a neutron star and a black hole, that produces gravitational waves and an outburst. With Roman's main time domain survey, we will have the capability of finding those events even independently of LIGO. So astrophysics, including synergies with LIGO, considering future synergies with LISA, actually is already an intrinsic part of our program. And we talk about the cosmology and the exoplanet demographics because they're named things that drove the design of the observatory. But everything that we have done in how we design the surveys has been to optimize for science in every area.
I think I'll add two other things. I think one, at the level of our fleet in NASA Astrophysics, we've got two other missions that are designed to be synergistic for LIGO as some sort of the driving cases. One is an Israeli-led mission called Ultraset that we're a partner on, and that's launching later this decade. The other one is Starburst, which is one of our small sats out of our Pioneer program that focuses on small sat astrophysics capabilities. That's a family of missions, not just including Starburst, but many others that focus on this sort of emerging capability in the commercial sector to do replicated, not just small sats, but now we're seeing detector fields, even telescopes are things that are currently being developed in the commercial sector where they can't do a Roman, but they can do some specific part of astrophysics at a more platform level. And we're even looking at concepts where, you know, if you built 5 of the same observatory, what kind of view of the sky does that give you, for example, to follow up quickly on something that goes boom in the night? We're looking at those things. Those applications in the near term or historically have been more focused on other domains of science than astronomy, but those capabilities are getting to the point now where there are astronomical applications for them.
Great, thank you. And with that, that is all the time that we have for questions today. So if you had a question that we unfortunately weren't able to get to, please do reach out to NASA's media team, and we'll be happy to help. But thank you very much again for tuning in and for all the questions today. And make sure to follow along with Roman's launch, currently targeted for no earlier than Sunday, August 30. You can learn more at nasa.gov/Roman. Thanks again for joining.
It's a huge accomplishment for us and this entire team who's worked very hard for many years to put this telescope together.
The Roman team is just amazing. They delivered the exquisite observatory we promised, and they did it ahead of schedule.
The success of this mission is due in large part to the efforts of the Roman Systems team.
It's been a marvelous team, and I was fortunate to be part of it.
It has been an incredible honor to work alongside this talented, dedicated, hardworking, and exceptional Roman Space Telescope team.
I couldn't think of a finer group of people with whom to take this journey.
It's been like our family for the last decade, and now it's leaving.
I'm proud to have had this group of people work alongside me on this challenging and rewarding project.